Okay. So the first thing that we'll look at really quickly is just the spin echo material. And these were our learning objectives for that. So one of the things that you should understand at this point is different sources of off-resonance, right? So who wants to describe quickly what off-resonance even means?
Dephasing makes the phases go off for the long frequencies.
Right. So what causes something to be not at the longer frequency? The sort of target. So T2 stars, there's something tucked in there that's the star component, right? T2 is really more about relaxation. But what makes something off resonant? Just any spin to be off resonant. What has to happen? There has to be something off with B0, right? So we always think of B0 as being, and then omega 0 equals gamma B0, right? The Larmor expression. We think of that as being on resonance. If your spin frequency matches gamma B0, you are on resonance, right? And if for some reason the field where your spin that you care about is slightly different than the target field of B0, you're off resonance. Now there's lots of reasons you could be off resonance, right? And at least the lecture material covered a few of those. Who wants to name one or two? I think we have 3 or 4 that we could easily talk about. What's a source of off resonance? We sort of alluded to one already. So chemical shift, perfect, right? So at the chemical level, there could be something that shields the protons, and they process at a different frequency, and are consequently off resonance, right? What's another source of off resonance? We had one already, right? Where we said B0 is not perfect. So if your B0 field is not perfect, then you'll be off resonance as well. What's another source of off resonance?
Susceptibility.
Susceptibility, right? So the ability of the external magnetic field to sort of permeate or get into the material itself changes as a function of the material's susceptibility. Air has a different susceptibility than water. And as a consequence of things like air-tissue interfaces or air-water interfaces, you have a susceptibility gradient, a difference in susceptibility, and you'll have a discrete difference in the field. The actual field in the tissue will be slightly different in air versus water, and that causes any deviation from B0 is a source of off-resonance. So those are the 3 that we sort of maybe most commonly encounter. But then there's one more source of off-resonance that we actually generate or create ourselves very actively. What's that? Gradients, right? So the application of a magnetic field gradient will produce a range of resonance frequencies. Some, those say an isocenter, will remain on resonance, and others will be distant from that on resonance frequency, and we could think of those as being off resonant. Now, at the end of the day, what on resonance means is that it matches the frequency you care about. And you may, in fact, not exactly care about the omega 0 equals gamma B0 field or frequency. You might care about some other upfield or downfield frequency because of the experiment that you're trying to do. So off resonance basically just means off from the resonance frequency that you're probing, interrogating, caring about. So you were actually getting to this a little bit, the second one, which is explain why off resonance gives rise to apparent signal decay and why it's reversible. So this comes into the concept of T2 star, right? So you can have sources of off resonance give rise to spin dephasing, right? And that spin dephasing, if it's due to a local source of off resonance, can actually be corrected for example, refocusing. I'll show you an example in just a little bit about the third point here, which is the difference between T2 and T2 star. But probably one of the main things to remember is that T2 is irreversible, right? T2 losses are irreversible. We don't know how to undo anything about those. T2 star losses, there's actually a reversible component there that we can deal with, say, in the context of a spin echo. I won't spend too much time talking about free induction decay signals. We don't use them a lot in conventional imaging. There are some interesting and esoteric uses for them, but they're not sort of central to this course, so we won't spend too much time talking about that. It'll show up in one of the slides, I think, today. And then the second to last one here is that we should be able to define a spin echo and the utility of the refocusing pulse. And I think you've seen this, a few times at this point. You saw it, some of you first in 205, and then it was in the lecture material, and then you saw it again in the problem. So I'll go over it quickly, but we won't spend too much time on it. And then one of the most important things to sort of appreciate, I think, is sort of how it is that we generate contrast in the MR signal itself. There's sort of two main principles to the MR, or two main components maybe to the MR signal. One is contrast, and one is spatial information, right? And so far we spent a lot of time learning and understanding how to manipulate the contrast as a function of things like T1 and T2 or T2 star, and things that we manipulate, like the TE and the TR. You should appreciate sort of the echo expressions for how the signal amplitude depends on things like T1, T2, T2 star, and consequently how to change the sequence parameters, the TE and the TR, to give you proton density rating T1 or T2 rating. We will look at that a bit as well. So this we talked about a little bit already. This is off resonance, right? And we talked about these different sources of off resonance already. The consequence of off resonance here, sort of towards the bottom, is that it leads to a loss of what we call spin phase coherence, right? Ideally, we want all of our spins pointing in the same direction. This is going to give us the best superposition of those spin magnetic dipoles and give us the strongest signal induced in our coil. But as they fall out of phase with one another, which will happen when there's the presence of some source of off resonance, then the total maximum signal amplitude available to us decays. Usually we're concerned about what's happening within a voxel or what's happening within a pixel. And that's an interesting concept because that means you can actually control in some ways the signal intensity by having smaller voxels which will have less signal dephasing. And that could be a way of regaining the signal. So sometimes higher resolution imaging actually has better signal properties than you might expect. There's different things that GRE can do to sort of deal with off resonance. Probably the most common one, which is done on a patient-by-patient basis, sort of subject-specific basis, is so-called field shimmy. The field's not perfect, we know that. We can make some quick estimates, and we can actually tune the field slightly so that it's more well-matched and more uniform for that particular subject. That can be really important for minimizing artifacts in some images. Susceptibility manipulation is much less common. There are people looking at sort of susceptibility pads, things that you could wear around your body that could potentially help with minimizing susceptibility gradients, but those are still relatively esoteric applications. And then probably the most common thing we do to deal with off resonance is use refocusing pulses, and that's central to which of the two principal pulse sequences? The spin echo sequence.
A question for the susceptibility gradients between different materials. Is it similar to refraction, where if you get something that's sort of in between them, it reduces total loss? Or how exactly is that permeation being affected by these gradients?
I wouldn't try to draw an analogy to refraction. Are you asking about how the use of some material can sort of help this problem?
Yeah, if we put it on the slide.
Yeah, well, right. So let's pick not a completely maybe practical example, but your airways, for example, whether it's your auditory canal, sinuses, trachea, whatever, they're air-filled, so you necessarily have a susceptibility gradient in those spaces. If you could fill those spaces with something that had a susceptibility matched to tissues, you could do away with that susceptibility gradient. How would you go about doing that? Well, there are certain fluids, for example, that you could fill an airspace with that would help match the susceptibility between that otherwise air-filled space and nearby tissues. When is that done practically? To be honest, the best example I can think of right now is for prostate exams. So they'll actually use an endorectal coil. Bowel gas can be a problem. And if you can susceptibility match everything in that space, then that can improve the language quality. So this is, I think you probably have this picture in your head already, but this idea of Intravoxel spin dephasing, and just trying to draw out the idea. Here we go. So this is, on the left-hand side, spins that maintain coherence, and on the right-hand side, spins that fall out of phase with one another. And so obviously, if they maintain spin coherence, then they generate a strong and sort of collective flux through that nearby coil. And so the Larmor frequency sort of continues with high amplitude for sort of the entire interval that's shown here. On the right-hand side, as those spins fall out of phase with one another, ultimately pointing in sort of all opposite directions, or however you want to say it, then their net sum is going to be near zero, or even zero. And so by the time they're completely out of phase, so to speak, they don't induce a net flux in the nearby coil because there's an equal amount of, say, positive and negative flux through the coil at any point in time. And so this is why signals decay as a function of Intravoxel spin dephasing. So in general, we don't want this effect, right? Because this causes signal amplitude losses and then overall sort of image quality or signal to noise losses. And there's different ways to deal with this, but somehow you have to deal with that source of off resonance. The most practical way of doing that is with the spin echo sequence and the refocus sequence. Okay, so let's talk a little bit about echoes. So quickly, the free induction decay, right? This is the signal that's available immediately after, say, an excitation pulse, right? There is some transverse magnetization generated, and you could make use of it, you could measure it. The problem is that signal decays really rapidly as a consequence of T2. That's something we can never sort of get away from. That's the sort of spin-spin level interaction, right? But then also so-called spectral or frequency distributions. And so we know that there can be these micro-scale B-field heterogeneities, that the B-field is not exactly perfect or homogeneous within a voxel at the scale of, the near molecular scale. And that's what we call the T2 star losses. It can be worse than that because you can also have what we call macro-scale B-field heterogeneity, sometimes called T2 star. And all that's meant to indicate is that there's something above the sort of chemical level, right? So this is sort of a field level effect, but at the voxel level. We always care about scales in MR, right? Time scales and B-field scales. And so we can appreciate that it's in the presence, if there's the presence of iron inside some voxel, that can cause some, that's a source of off resonance, and that gives rise to T2 star relative to, say, T2. But if there's another source of off resonance, a B-field gradient inside your voxel, then that's what we refer to as macro scale B-field heterogeneity, so this T2 star. And so that FID signal decays quite quickly. And in fact, those macro scale B-field heterogeneities could, for example, arise through the application of a gradient. A gradient will dephase your signal very quickly. And that's sometimes a very useful thing, but it's a fact. Gradients will dephase your signal. They are applying a source of field homogeneity or generating a source of field homogeneity. And we know that imaging, and we'll talk about this hopefully at the end of this lecture, that imaging requires some certain delays. We don't just excite and then sort of magically image instantaneously, right? There's a period of gradient waveform application that we use for so-called slice selective rephasing, phase encoding, readout prephasing, things we haven't talked about specifically yet, but so-called delays that mean we can't make use of that FID signal immediately if we want to do an actual imaging experiment. And so the way I like to say it is that echoes let us buy some time. That FID signal is gone pretty fast. And so what are echoes? Well, echoes are these two-sided NMR signals, right? The first half comes from some source of refocusing, and the second half comes from additional dephasing. So we sort of refocus the signal to its peak amplitude, but then some sources of off-resonance cause that signal to decay. And in this course, we'll basically talk about two kinds of echoes. Radio frequency echoes, which arise from multiple RF pulses. And the easiest example there is the spin echo, right? You play a 90 pulse, and then at some later time, you refocus it with a 180, and at a slightly later time, you generate the formation of a spin echo, or a radio It only requires the application of multiple radio frequency pulses. The other option is the gradient echo, and that arises specifically from magnetic field gradient reversal. Right? You have, say, a negative gradient turned on, and then you flip the sign of that gradient, turn it on in a positive sense for some period of time, and you can actually help form an echo in that way. And so we'll talk a little bit more in detail about both of these spin echoes and gradient echoes. So this should be a figure that's pretty familiar at this point. On the left-hand side, we have a 90 pulse, and this is what we've been saying, sort of for this lecture and previously, that you can generate some transverse magnetization immediately, but it decays away by T2 star, right? That's the sort of the worst case decay rate, if you will, and the gradients, which in this case aren't actually shown, but that leads to rapid dephasing of this FID. If I didn't write and gradients, I could have just written T2 star star. The T2 star star infers that there's the T2 star losses plus these additional losses from macro level field inhomogeneity. And so the fun part of the spin echo sequence is that, and it must have been a real surprise to the first guys doing these experiments, right? Because it seems as if the signal's all gone, and then you play an RF pulse twice the amplitude, and all of a sudden your signal comes back, but it doesn't come back until later, right? So I think the first guys to have done these experiments must have been kind of blown away for a little while. But what you see is the formation of the echo on the bottom there, right? So there's the reversible components can rephase, right? There's some losses, right? So the signal amplitude at the formation of the spin echo is lower than it is immediately after the 90. The strongest signal you can get is the very, very beginning of the FID, right? You play a 90 pulse, it puts all your magnetization on the transverse plane. The problem is it's gone so quickly, it's hard for us to do much with it. If we play this 180 pulse, then we can reform, we can undo those reversible sources of off resonance, but then those irreversible sources take over again, and they cause additional dephasing, and so then the echo sort of falls off again. But it has this sort of symmetric appeal. And we basically call it an echo because there's an event, the 180, and it takes a little while before the signal sort of comes back into the receive system again. So there's this delay. When it comes to the timing of these things, you can see on the left there that the FID decays really quickly, something like T2 star or even T2 star star, right? And that the envelope on the spin echo signal is more like T2. You saw in the derivation for the spin echo expression, both in your homework and then spin echo lecture itself, that this phase term gets reversed, right? And as a consequence, the off resonance phase cancels at the echo time. And so we could ask ourselves these questions. I think we've maybe even talked about this before, but from a practical perspective, when we sit down at the scanner, we can adjust the TR, right? I can punch in 1,000 milliseconds for the TR. I can punch in 10,000 milliseconds for the TR. What happens in my actual pulse sequence when I tell the computer to use a longer TR? What's actually happening to the timing of my RF pulses? When is it going to play the second 90 pulse? Just according to the TR that I punched in, right? And so that's, we're dictating what the TR is, and that's just telling the system how frequently to play the excitation pulse, the 90 pulse, right? And we probably asked that question very well. That's what I was getting at. Maybe it's a little bit easier to answer the second question, which is how do you adjust the TE, right? So now you want to pick the TE, you sit down on the scanner, and you say, oh, let's use a 40 millisecond TE. What does the scanner do to adjust the timing so that the echo forms at 40 milliseconds? What about the 180?
It'll adjust what it is.
Yeah, so if my TE is 40 milliseconds, when do I play my 180? 20, right? So it's just the 180 happens halfway in between excitation and echo formation, right? And so you'll see this, we'll work on the scanners next week, right? We'll have the lab. And so you'll get an option to sort of play with these things, but behind the scenes, it's good to recognize that while we're punching these timing parameters, what's happening behind the scenes is, of course, adjusting the timing of the sequence of the RF themselves. This is the RF pulse operator that we've been using in this class to sort of as one way of representing what happens to the spin system through the consequence of an RF pulse. And we have to pick something about the phase, and we have to pick something about the flip angle. Here we really, in the case of a refocusing pulse, you can see I have alpha is pi, so a pi pulse is a refocusing pulse, or a 180 pulse. In that case, I still have this free variable of my phase, right? And so I can choose to rephase my magnetization in different ways, because I can choose to have the phase of my RF pulse, say, about the x-axis, in which case maybe I'm flipping like this, or I can choose the phase to be around, say, my y-axis, and I can be flipping my magnetization about the y-axis. There's different reasons why that might be a useful thing. The effect is that the axis about which the magnetization will form the echo will be different, right? So when these spins rephase, they're going to rephase, say, along the mx direction. And that may or may not matter to me, but I could use a different refocusing pulse, and I could have them rephasing along the my axis. The reasons why you might care about that, we won't get into it in this specific class, but it's a possibility. And so we can pick the flip angle, and we can pick the phase to be 0 degrees, and then this RF pulse operator is really simple. It's just zeros, ones, minus ones. And that can act on the state of the magnetization to give us new magnetization. And that's all I'm showing here, is that it will actually reflect, if you will, the transverse magnetization about, in this case, the x-axis. We could choose a different RF pulse. In this case, it's still a pi pulse, so it's still a 180 refocusing pulse, but now it's phased over the pi by 2 axis, so the y-axis. And in this case, the magnetization would just be flipping about the y-axis instead of flipping about the x-axis. When it comes to having the spins form an echo again, it doesn't really matter to us that much if they're forming an echo at a time when they point along y or at a time when they point along x. There's some applications where maybe we care, but for this class we basically don't. So the refocusing pulse, as far as we're really concerned, is relatively independent of the phase of the RF pulse that we choose to use. And in most pulse sequences, when you sit down at the scanner, you don't control that. There might be something behind the scenes that was chosen for a particular reason, but we don't generally control the phase of that pulse. And so then this is the simple animation that we've been sharing for what the spin echo sequence really does, right? I'll try to back this up one more time. Oops. Sorry. And so, yeah, the 90 pulse that tips things down, and now they're dephasing, and it's a refocusing pulse that flips them over. And as those same sources of off resonance come back together again, they push the spins to point, say, in the same direction. And all that happened at the end here was the 180 pulse, the timing of the 180 pulse was moved out, and that will affect where you are along the T2 decay curve. So what's not shown in that animation, what's not really shown in this animation is actual signal decay, right? All you're seeing is what happens to a set of spins that are exposed to some source of off resonance being flipped over by the 180 and then forming an echo at a later time. And then as the 180 pulse moves out, you're collecting the signal at different points along the T2 decay curve. So that's the off resonance, the refocusing, off resonance brings it back together, and then different elements, or different echo amplitude is a function of what the echo time will actually be. You would have seen it in the derivation that was in the spin echo lecture, but I think it's important to appreciate that it's the same sources of off resonance, right? So during this first interval t, there are sources of off resonance that cause the spins to fall out of alignment with one another, right? And what's really interesting, I think, about the spin echo sequence is now you flip it over like a pancake, right? And it's those same sources of off resonance, right? The same field is causing the same off resonance to be induced on those spins, but that will bring them back into alignment for a brief period of time before that off resonance causes them to fall out of alignment. Does that conceptually make sense? Yeah.
Did you play the readout gradient during echo?
Yes. Yeah, we haven't exactly gotten to that yet, but we'll be getting to that in kind of, I don't think even at the end of today, but in the next lecture.
Does it change the way that echo is shaped?
Very, very subtly. Yeah. And so it's kind of one of these remarkable things that I think one of the things that's so neat about MR is it's operating at very, very different scales, right? So very different temporal scales and very different magnetic field scales. And so the effects of the gradient are useful for doing what we call spatial encoding, but they're not really changing sort of the state of the magnetization itself. Subtly, but not hugely. Okay, so at the end of the spin echo lecture, and I think you guys have worked through this a few times, and I know I said it when we were working on the saturation recovery and the inversion recovery stuff. You'll have an example, something like this on the final exam, right? I think this is one of the sort of key components, principles of this class, is being able to keep track of what happens in the magnetization as a consequence of a series of some generally RF events. Maybe there's off resonance, maybe there's a gradient, these kinds of things. You had a homework assignment that was similar to this. You've seen a few examples in class. If you're not comfortable with those working examples, then reach out to me, reach out to the TAs, whatever. But the point I'll make here is that we can keep track of the magnetization from before and after time point 1, before and after time point 2, and we can say, well, what's happening at a particular time point we care about, the echo time, and then maybe what's happening at the very end of some interval, the TR in this case. And having worked through that exercise, this was a not terribly long expression that describes what's the state of the Z magnetization immediately before time point 4. Right? So what's the state of MZ as you get all the way down here? Why do we care about the state of MZ just before the next TR? I mean, it's sort of written there too, but go ahead. Right, so that's the state of the magnetization coming into the next TR. Right? That's how much MZ you have available to you that could eventually help you form an echo, right? What is MZ? I mean, this is trivial for you guys, I hope, at this point, but what is MZ immediately before time point 1? We just take it as M naught, right? And eventually we'll make it, you've seen the substitution too, sometimes we just call that rho, right? It's the proton density, it's how much you could possibly sort of have. And MR experiments are always multi-pulse experiments, right? We always have to play hundreds, sometimes thousands of RF pulses. And so it typically matters that we reach a steady state, right? And we've played a series of RF pulses until the amount of magnetization at the end of the TR is the same after we've done this, dozens of times. Sometimes it only takes 1 or 2 times, sometimes it takes dozens of times. Depends on the exact RF pulses and gradients and so forth. But we typically have to keep track of the magnetization to the end of the TR because, as Tyler was saying, that's the initial condition for the next TR. And so we don't necessarily care about this in terms of what it does for kind of image contrast, because it's not telling us about the magnitude of MZ at, say, the echo time. But it's still really important for us because it carries into what happens in, say, the next TR. So if you do use this as the initial condition and then follow it through to time point 3 for the second TR, then we end up getting this amplitude expression. So the amplitude of the echo, which is to say how strong is your echo signal exactly at, say, time point 3, maybe in the second TR. Then now we can see it depends on rho, which is the proton density, instead of being M naught. We usually make that substitution. And then this isn't too cumbersome, but you'll see that it depends obviously on things like TR and T1, and then also TE and T2. And this is having kept track of the magnetization, through one TR, then brought it in as the initial condition and said, well, what happens at my echo time? Because the echo time, and we'll talk more about K-space at the end of this lecture and the next couple lectures, but the amplitude of your echo really dictates mostly your image contrast. And so this tells us how contrast is sort of stored, or signal information is stored. I shouldn't say contrast per se. This tells you what's the amplitude of the echo, and the amplitude of the echo, or the signal that you can get from one pixel versus another pixel, is going to be different, because different pixels will have different T1s and different T2s. Now, that expression gets a little bit simpler if we just make one simple assumption, right? So if we just say that the TE is typically much shorter than the TR, for the spin echo experiment, it's a pretty good assumption. All right, what's a sort of ballpark TE for the spin echo experiment? It's ballpark. So engineering analysis, right? So 1 millisecond, 10 milliseconds, or 100 milliseconds? 10. Good. Okay? And so we know our TE is maybe 10 milliseconds. That's a good. You should be able to ballpark those things for this class for sure. What's a ballpark TR? Is it 1, 10, 100, 1,000? Or milliseconds? Yeah. So 1, 10, 100, or 1,000. I'm going to go, I hear 1,000. 100 maybe, 100's on the short side, but 1,000 or more is good. And then in that case, you sort of meet that TE is much less than TR. Right? If your TE is 10 and your TR is 1,000, then you're off by a factor of 100. That sort of meets that criteria in my mind. And so we can look at that expression, and we can just look at its limits, right? We can say, well, what happens if I have a short TE and a long TR? And so this pulse sequence right now has a short TE, right? My 180 pulse comes pretty quickly after my 90, and I consequently form an echo pretty quickly. But then I've waited gobs of time until I play that next 90, right? If I look at that echo expression on top there, and I look at the limits of when TE is really short and TR is really long, what is that expression reduced to? What happens if TE is really short? It becomes like a 1, right? And what if TR is really long? It's like a 0, right? And so then I just have something like rho, right? That's proton density. And so we never really get a pure proton density weighted image, right? We might want one, but the best we can do is have kind of the shortest TE we can achieve, and there'll be some limits on exactly how short we can even get anyway. And then we also don't want practically long TRs, right? And there's sort of diminishing returns, right? Once your TR is many times longer than your T1s, then it's not helping you much anyway. And so you might as well call it quits at 5 seconds or something like that. So we can move forward, right? We can bump that 180 out. This is what Tyler was talking about. If we want our echo time to be later, we just push out our 180, form an echo at a later time. Here we've got a 47 millisecond echo time. And just delaying that 180 refocusing pulse obviously delays the TE. Then we can keep playing this game. You can do this on the scanner next week. We can choose different TEs, keep the TR constant. And in this case, you'll see the image contrast is changing pretty dramatically, just as a consequence of changing the timing of that 180 pulse, right? Until at the very end here, now we've got a pretty different source of image contrast, right? At this point, we've got our TE is long, right? And our TR hasn't, in this case, maybe changed very much, or hasn't changed enough. And so you can see here that the CSF, for example, the really bright stuff here surrounding the brainstem or the spinal cord at the bottom or around the very top of the cortex, that's all CSF. CSF is a fluid with a long T2, and so it's clear in this image that long T2 is bright on a T2 weighted image. So why would that be the case? Well, when you have a long TE, those things with really short T2s, they decay, right? So if you have white matter and gray matter that have substantially shorter T2s than CSF, they've had a lot of time to decay from when they were excited, refocused, and finally formed an echo. And so those signals are disappearing quickly. Whereas CSF is happy to kind of hang out. It's got a T2 of 180 milliseconds and it's just slowly decaying. And so those long T2 species, they don't decay very fast, so they stay bright on a T2 weighted image. So you should understand mathematically, that's a good expression to know its origin of and to understand why it exists, right? And then you should appreciate why that expression would in fact tell you that long T2s are bright on a T2 weighted image. This is a very sort of common thing to remember for understanding and interpreting images. Because you might, for example, acquire an image that has a long TE and a long TR, right, as a way of getting a T2 weighted image. And then when you're imaging someone, you say, oh, that's really strange. There's this really bright pocket of stuff in the middle of their abdomen. That must be fluid. So there's this sort of reverse engineering process that happens once we agree that we know and understand the math. So that's how it can be used sort of more in a forward sense. Okay, so that's it for spin echoes, unless there's questions. Yeah? Okay, so I'm going to do the same thing for gradient echoes, but I think I put in fewer slides because some of the previous stuff sort of led in even to this stuff. So for the learning objectives here, we'll talk through these. I think this is a pretty good exercise. So one is to describe the pros and cons of gradient echo acquisition, especially in comparison to a spin echo sequence. So who wants to name sort of an advantage of the gradient echo sequence? Why do we use it? It's faster. Why is it faster? Like what's one reason?
Don't have to wait for the refocusing.
Yeah, so is there refocusing?
No.
So there's no refocusing. And so, and I guess maybe it's always sort of hard to know how to get the answer out, right? It's a faster sequence because something about it's shorter. What's shorter, typically? TR, that's all. Yeah, no, I know. Like, I know you know. It's just teasing it out, right? Great, yeah. So it tends to be a pretty fast sequence, and that's a good thing. What's another advantage to that sequence? Yeah, so why would small flip angles be good? Could be, yeah. And so low flip angles, lower energy deposition in the body, so that could be a good thing to get you below a SAR limit, or just to simply make the scan more comfortable. Actually, we're working on a project right now to develop protocols for so-called conditional devices, right? Pacemakers, neurostimulators, these kinds of things from manufacturers have SAR limits, but people don't necessarily know how to protocol exams for patients with those devices. And it oftentimes comes down to SAR, and you may have to make a substitution, for example, from a spin echo sequence to a gradient echo sequence because the gradient echo equivalent would be lower SAR. So it's not always the case that gradient echoes are low SAR sequences, but they're typically lower SAR than a spin echo sequence, for example. Maybe what's a disadvantage to the gradient echo sequence? No refocusing pulse, right? So why? So how would you describe that as a disadvantage? Why? Like, why is that a bad thing?
We can,
No. You got it.
you can only have T2, oh, so your T2 star,
Yeah.
T2 star.
Yeah, and so without the refocusing pulse, then you're inherently T2 star dependent, right? And that's either a good thing or a bad thing. It sort of depends. T2 star contrast is useful for drawing out off resonance deposits of iron, blood products, other iron products. That can actually be a useful thing. So sometimes it's hard to say something that you can sort of spin it as a positive or a negative depending on what you're trying to do with it. Okay, so I think that's a reasonably good discussion there. Understand why GRE can't acquire true T2 contrast. What's the main thing that's missing that limits us from getting T2 contrast? Refocusing. So yeah, and this is a good one too. So explain why. Who wants to explain maybe what a spoiler is and why they're typically used with a gradient echo sequence? I know Tyler probably knows. Aiden?
Just a bunch of sort of random or multiple gradients applied at the end right before TR to the transverse magnetization.
Yeah, and so at the end of the TR, we can spoil or get rid of our transverse magnetization so that it doesn't there's no initial transverse magnetization going into the subsequent or next TR. Why is that a useful thing? I mean, one reason is to say get rid of artifacts. That's good. There's maybe a more important reason. Yeah, right? We always want to scan fast, right? So if you can, the other way to spoil is just to wait for the transverse magnetization to decay, right? But that could take many tens of milliseconds before it's acceptably gone. Whereas you can accelerate that dephasing through the application of the gradient, and the transverse magnetization is gone, then you're ready to fire another RF pulse again, and that means you can scan faster. So gradient echo sequences are also typically associated with fast scanning, and in part because of the use of these spoiler gradients. We'll see this in a little bit. I forget if this came up already, but do you guys have a concept of how to calculate scan time? We want to know how long is it going to take to acquire this image, right? We'll get to this one. I haven't covered it yet here, but I know I have one slide about it, so we'll just wait to get to that. We talked. I know Mike showed you some of this about the optimal flip angle calculation for gradient echo imaging, and I'll talk about that in just a second. There was a name for it. Does anyone remember? Ernst angle, right? So there is the one sort of different, interesting thing about the gradient echo sequence is you control not just the TE, the TR, but also the flip angle, right? And then the question becomes, well, how do you choose those things, right? Well, choosing TE and TR is actually very similar to the spin echo expression. Whether you want it short or whether you want it long, actually, it's the same governing principles. How you choose your flip angle is a little less obvious because of how the flip angle enters into the gradient echo expression. We'll see an example of that. And then I'll talk about this super fast at the end, but I think this is a really cool thing that, especially for those kind of research-minded folks thinking about MR, the idea that because fat and water process at different resonance frequencies, right? As a consequence of what? Why is fat different? We talked about this a second ago. Chemical shift, right? So fat has protons in it, obviously has hydrogen in it rather, but that's chemically shifted by its surrounding milieu of carbons, so that it has a slightly different frequency. It's shielded in a way. And so fat and water will have different precessional frequencies. And in fact, it's more complicated than that because fat has a spectrum of frequencies and water is sort of a line, or it should ideally be sort of a single frequency or a very narrow range of frequencies. But bottom line, there's some really neat tricks we can play to separate out images so that we can make a picture of just fat or make a picture of just water. And that, again, diagnostically could be a very useful thing. Typically, diagnostically, we don't care too much about fat. If you end up with an unusual tumor, but it's a fatty tumor, those are usually very benign, and maybe you don't prefer to have it, but you're probably going to be fine. Whereas other tumors that are non-fatty tumors, that can be a very different diagnosis and a different course of treatment. So fat-water separation is really important for tumor diagnosis. It's important for liver disease evaluation now, and all kinds of things. So really neat sort of emerging field. So here I'll talk quickly about the differences between T2 and T2 star. On the left hand, this looks similar to a figure that we had before. So here we have signal losses from so-called spin-spin interaction, right? And so as those spins are precessing around, they're staying on resonance with one another. They're not falling out of phase with one another, but they are getting smaller and smaller in sort of overall vector of magnitude, and that's the consequence of T2. T2 causes decay of the signal, but not dephasing per se. But if you couple dephasing with decay, the dephasing is sort of the star component, if you will, and then the decay is the T2 component, if you will. And now my signal is going to decay even more rapidly than it would in the absence of this, of the T2 star losses, if you will. And so T2 star is going to be a shorter time constant. It's going to result in faster decay of the magnetization. But it is a combination of irreversible things, the T2 stuff, and then it's also some reversible stuff, the star stuff. And the star component is what can be refocused with the refocusing pulse. But in the absence of a refocusing pulse, like the gradient echo sequence, then you're dependent on so-called T2 star contrast. And so this is what the pulse sequence looks like, or one example of it. And this is material that Mike would have gone through with you just about a week ago. And so the sequence looks a little bit different because we don't have a refocusing pulse. We basically have an excitation pulse, which is going to be, it could be any sort of flip angle. Typically it's a handful of degrees, 5 degrees to 30 degrees or something like that. And then how the echo itself is actually formed is not entirely as obvious, but it's through the application of this sometimes called frequency encoding gradient, where we play a negative gradient and then we can reverse and reform the echo at a slightly later time, but through the application of not a negative but a positive gradient. And the movie on the bottom shows the excitation, then some off resonance, and then the gradient forcing them back into alignment again. And then that flash is supposed to be the echo. And so that's the excitation. There's some gradient off resonance that causes things out of phase. The gradient reversal brings them back in phase. And then the second half of that gradient brings them out of phase again. So that's this gradient, then coming back into phase, and then falling out of phase on the third part of the gradient there. So that's one animation of how the gradient echo signal is formed. So there was a slightly different approach to getting to the solution of what the Z magnetization looked like, because we wanted to look at a steady state solution. Mostly because in this case, we're playing the RF pulses really close together in time, and it takes some time to build up to an actual steady state. It didn't work through sort of the calculation of how many RF pulses it takes, but it's typically dozens of RF pulses before you reach so-called steady state. And the result that we sort of principally care about, at least, is this amplitude of the echo expression. So this tells us what is the amplitude of the signal as a consequence of the proton density, the T1, and in this case, the T2 star. Those are the things that we don't control, right? And then the things that you do control include the TR and the TE, and those terms, for the most part, look similar to the spin echo expression, especially all the stuff in the numerator. What throws things off a little bit and throws your intuition off a little bit for how to do the parameter assignment is the dependence on the flip angle, the cos alpha term here and the sine alpha term there. I know Mike worked through some simulations to show you sort of this, how you can get different amplitudes of the gradient echo signal as a function of the flip angle that you choose. And so I think the key to remember here, and this will be important for, I think, your second laboratory, but we're going to give you a terrible protocol, and your job will be to take that terrible protocol and actually try to tune it up and make it a good protocol. And I can guarantee you that you won't be using the optimum flip angle from the get-go, right? And so one of your jobs will be to figure out, well, what flip angle should we be using? And this is going to be your best way of guessing at that. And we use this, daily, right? So when we sit down to a protocol, we probably know what the TR is. That was chosen for usually a consideration related to scan time. And now you want to know what flip angle to use. Well, you probably know something about your T1s, and then all of a sudden now you know what flip angle to use. And what I will say is, and these pictures sort of show it, right? So this is mapping out the Ernst angle for muscle in blue and for fat in yellow. And if you want the maximum signal, then the maximum signal for muscle is going to happen at about 10 degrees, and the maximum signal for fat is going to happen at, say, 20 degrees for a short TR of, say, 5 milliseconds. And I guess maybe a take-home point here is, yes, there's an optimum, right? Higher and higher flip angles are better. There's a tendency, I think, at least initially, to think, oh, well, a 90-degree pulse must be better, right? I think Mike worked through some examples to show you that if you tip over by a 90, but you only wait 5 milliseconds, the magnetization's barely recovered, right? And then you tip by 90 again, and eventually you've just saturated the magnetization, so there's very little ability to generate a useful signal. Whereas if you play just a, say, 10 or 20-degree pulse and generate a little bit of transverse magnetization, that'll actually give you more signal per unit time. So what's the point? Well, the point is the Ernst angle tells you there is an optimum, and you should use it in general. And I think the other take-home is that the Ernst angle is typically on the low side. It's usually between, say, 5 and 20 or maybe 30 degrees. It's not going to be 90 degrees or 180 degrees or anything like that. So keep that in mind generally, but then also for the second. Okay, so this was, yeah, right. So this is just comparing the spin echo expression to the gradient echo expression. And I said this a second ago, but there are components of which are quite similar, especially in the numerator, right? They both have this sort of linear dependence on proton density. They both have this similar dependence on TR and T1, right? It looks mathematically identical. What's different, say, on the back end here, is the dependence between TE and T2. The only real difference being that the gradient echo expression depends on T2 star rather than T2. And then you have to take into account, in a way that's not obvious unless you track through all the magnetization, how the flip angle sort of folds in. But the basic take-home is that the kinds of TEs, the kinds of TRs you want to get proton density weighted images for a gradient echo sequence or spin echo sequence are similar. We're still looking at trying to get this term to go to zero, or the TE by T2 term to go to 1. So that we can get the specific weighting that we want. And so that's where we can make a comparison now between, say, the gradient echo parameters that we would use and the spin echo parameters that we would use. And you'll see, for example, if you want a spin density weighted image, in both cases, gradient echo or spin echo, you need a so-called short TE, right? You want a short TE to minimize T1 or T2 contrast. Short TE is related to T2, right? So we don't want that much T2 contrast. We want to tighten up the TE as much as we And then again, for spin density weighted contrast, we don't want T2 to play much of a role, nor do we want T1 to play much of a role. If you want to knock out the T1 dependent terms, then you typically will need a long TR. And that's same for both the spin echo sequence and the spin echo sequence and the gradient echo sequence. And so, for the most part, how you choose your TE and TR, it's the same between these two sequences. The slightly different component, of course, for the gradient echo sequence is that you're only going to get T2 star dependence, and you have to know what flip angle it is. And that's not obvious unless you sort of really carefully work through the mathematics. Now, those are sort of the simple terms that we use for describing how to get spin density weighted imaging. So if you talk to the medical residents, they'll remember that spin density is short-long. Like that's just how they'll think about it, because rather than working through the exponential expressions, they just know short TE, long TR, spin density weighted, whether it's gradient echo or spin echo. The subtlety to all of this is the actual timing parameters. And so the actual timing parameters that are sort of possible with the gradient echo sequence versus the spin echo sequence are slightly different, which is to say a short TE might be will definitely be less than 5 milliseconds for a gradient echo sequence, but it might be 10 or 30 milliseconds for a spin echo sequence. So what short actually accords with is a little bit different between the true gradient echo sequence and the true spin echo sequence. And that's just a function of sort of the actual timing that those sequences can kind of easily achieve. Okay, so questions about sort of the signal equations for spin echo or gradient echo and how they're useful and sort of what these parameter tables sort of mean. I wouldn't expect you to ever memorize these kinds of numbers, but ballparks are good, or they could be useful for you for sure. It's definitely useful to be able to get quickly to these things, which fall out of those amplitude echo expressions. Yeah? I think, yeah, so I'll talk about one more thing and then we'll take a short break because I need to get less water. There again, Mike covered this at least briefly, but I want to go through it one more time. Frequently, pixels can be a mixture of both fat and water, right? Why would it be the case that a pixel would be exactly just fat or exactly just water? And the pixel intensity is the vector sum of whatever's happening to the fat spins and whatever's happening to the water spins. We're just receiving a signal from the pixel, and we can't quite distinguish stuff inside of a pixel, right? And so the picture that we have here, in this case, this is showing fat and water, say, both residing, say, 50% of the pixel is fat and 50% of the pixel is water. And in this case, that's showing that the bulk magnetization is in phase with one another. Because of chemical shift, they will be processing at different frequencies. If they process for just the right amount of time, they'll come back into phase with one another, right? It's like a beat frequency. And so when they do happen to come back in phase with one another, if that's when I happen to acquire my echo, then it'll appear that the water signals will add together and give me a nice strong signal. And we call that an in-phase image, water and fat. The timing, which really comes in through the echo time. The echo time is chosen such that fat and water are in phase. Those signals will superpose, add together, and give you a strong signal component. Which is to say, when they're in phase, you add them together, you get something greater than 0. What's the other possibility? Well, one other possibility is that you continue to let things process up until a point where they're perfectly out of phase with one another, right? Just by choosing the timing a little bit differently, fat will be perfectly out of phase with water. And now the vector sum of my magnetization coming from fat and the magnetization coming from water is going to give me something that's basically 0. How precise or exact that is depends on the exact timing of the experiment and exactly how on or off resonance water and fat are from one another. But we have this concept in mind of being in phase and in opposed phase. And this is actually really cool. What controls the phase between fat and water is really the echo time. How long did you wait from excitation? Everything got excited at the same time, right? So we pushed fat and water down, and now we're waiting. Water's doing one thing and fat's doing another. If my echo time is now, they're in phase, and if I keep waiting and they're out of phase, and that's my echo time, then it's no good, right? And this is actually really interesting, right? So it shows up very discretely in our images. So on the left-hand side here, we have an in-phase image, and on the right-hand side, same slice, we have the out-of-phase image. And what you'll notice pretty discreetly is areas where fat and water, like where these blue arrows are pointing, that's a tissue boundary between some of the neck muscles and some of the subcutaneous fat. And so the pixels that are a perfect mixture, say, of muscle and fat, when they're in phase, they just give you a kind of consistent intermediate signal intensity between the bright of fat and the relative gray of muscle. On the other hand, if you have an opposed phase TE, so fat and water completely out of phase with one another, then at the time you acquire that image, there's a signal cancellation. Water and fat are opposed to one another, and it's a complete drop in signal for that particular pixel. And this can, in fact, be a useful diagnostic thing, because there are techniques where you can actually pull apart these signals. The gradient echo lecture didn't get into the details of this too much, but just as you can form a single echo through one gradient reversal, you can reverse the gradient again, form a second echo, reverse the gradient again, form a third echo, and you can keep going, except for the fact that these echoes are getting smaller and smaller and smaller in amplitude. So by the time you've gotten maybe 5 or 6 echoes, there's probably not a lot of data left or information left. But the point is that from the time of excitation to the formation of each of these echoes is slightly different times, and that means that fat and water will be at different amounts of, different degrees of being out of phase with one another. And so now there's a linear regression problem you can solve where you can actually estimate the off-resonance frequency between these two spin systems, and then actually estimate how much of that spin system is fat and how much of that spin system is water. And so you can get, I think I have it in the next slide here. It's tiny. So on the bottom here, if you have all of these different echoes at different, if you have all these pixels, say, at different echo times, you can put them through a so-called fat-water reconstruction engine and reconstruct images that are water-like images on the left or fat-like images on the right. And again, this is a sort of increasingly common thing to try to do clinically. Both there's a lot of research developments in this area, but there's also increasingly clinical applications in this area. Probably one of the most interesting, from my perspective right now, is evaluating fatty liver disease. Very, very common. The degree of fat in your liver is bad. And so being able to measure that non-invasively, you don't need a biopsy, you don't need some other technique, and actually get a measurement of what % fat is someone's liver, that can be a very useful diagnostic criteria for understanding someone's liver health. And MR seems to be basically the best way to do that these days. So shown a little bit more clearly, this is sort of all these things taken together. So we do have other ways of dealing with fat in imaging in general. There are so-called fat saturation techniques where we can try, for example, knowing that fat and water have different frequencies, resonance frequencies, we can try to excite just water, or we can try to excite just fat. But those generally work pretty imperfectly. And so here you can see an example of trying to saturate fat. And you can see that the fat in the neck back here and up there is suppressed in signal intensity, but it's certainly not absent. On the left and right images here, there's a fat-water separation technique. So this shows the sort of a very well-resolved water image, and this shows a nicely resolved fat image. So completely sort of separating out the pixel signal intensities that are coming from water protons versus fat protons. And then that's just in distinction to, say, the in-phase and out-of-phase images, which they're useful, but they don't separate out those signal compartments as discretely, right? So here you can see subcutaneously you have some water, but it's really mostly fat. And so this is, again, a really interesting sort of diagnostic approach to breaking apart MR signals. Okay, so questions about sort of spin echoes and gradient echo stuff? I know it's a lot. I'm trying to sort of just hit the highlights and then sort of take questions as we go. You can definitely ask me questions right now. We'll take a short break, get a drink of water, and then we'll come back and try to talk, we will talk about the MR Signal Equation. This is actually, I think, one of the, maybe one of the more complicated topics for the class, but also one of the, I think, interesting, probably important as well. But let's take a short break and we'll come back to this.
now is purchasing.
Yeah, look, they usually take a year or two. They're free inspection.
Yes.
So,
Oh yeah, yeah, they're on.
no, for sure. But,
Yeah.
we want
And then basically you get filters, chipboard sign, and
to-
single
that's-
no. You just have to see. And I told the people at Matter Hackers, so they gave me new quote from today. So
So we have 30 days.
30 days, yeah. Because they're really quick.
Yeah, it's a design. He saw how it was last time. It's really bad.
Yeah, I already have the sole source justifications ready. I'm not sure if they need it because it's not the company, like we're not buying from the vendor, we're buying from, like we're not buying from, I guess, the company, we're buying from the vendor.
Yeah,
I saw her pulled out.
yeah, I think that's what we need.
Yeah, I did all the,
I think it has to do with
I know, true.
Five hours and
that may be.
yeah, well,
Just go with the cheapest quote.
then it's like 2 to 3 shipping.
Yeah, that would be the bottleneck.
Yeah.
Sorry, Fred.
Yeah, and it's 2 shipping.
Yeah, you said it was close.
Yeah, 2 hours. It's just below Amazon. So it said we can pick it up for all the rest. Yeah. Luigi and I made an outline for paper. Figure when we have a meeting.
Alright guys, so the plan now is to go through the MR Signal Equation. There's a series of relatively complicated derivations that underlie all of this. I don't know if you guys watch those online. I don't have easy way. I guess I could go to the YouTube counter and try to figure that out. Right? So I guess what I'll say is that material is there online. We won't, as a matter of time, go through the nitty-gritty of the derivations. I do want you to be able to understand and recognize the terms of a couple of the key expressions. And that's basically what I'm going to do now. So this is going to be kind of a high-level perspective that gets us down to really one of the most important expressions in MR. And so this next sort of, call it 30 minutes or whatever it takes, is I think one of the sort of key concepts in MR. So we'll spend the time that we need to get through it. It's probably going to be hard to ask questions, but don't hesitate, and I'll try to point out the things that I think you guys should know and sort of understand about this. Again, if you really want to see it sort of worked all the way through, then that's what the online lecture will help you see and get into the details. I think I won't spend a lot of time on the learning objectives for this one, so we can kind of get right into it. So you'll remember that this is sort of the overview of how we've been sort of working through understanding hardware components, and now we're sort of in this next kind of 30 minutes quickly moving through how it is that we go from a state of transverse magnetization, right, which we now have a pretty good understanding of how to manipulate through gradient echoes and spin echoes and RF pulse timing and TEs and TRs. Those change the state of the transverse magnetization at, say, the time of the echo. And that tells us how much signal we can get back out of the underlying tissues. The really tricky business is how do you go from this magnetization that's zipping around at the Larmor frequency, right, and that's inducing a coil in your current, to what we now call K-space. And so we're going to try to make these connections right now. How we go from transverse magnetization to, in fact, spatially encoded magnetization that gives us a voltage, that gives us what we call a complex signal, that eventually gives us what we call a K-space signal. There's a lot of kind of heavy-ish mathematical steps to go through here. We'll cover it again at sort of a higher level, and then obviously ask questions as we go. Or if you really want the nitty-gritty, then that is online. Where we're going to land, or where we should land, we'll see this exact same or very, very similar slide to this in about 10 or 12 slides. Again, would be at this point here. So this is the so-called MR Signal Equation. And it's a really important expression for MR because it tells us what a point in K-space represents, right? So we have this maybe loose notion that the data that we actually acquire with an MR system is so-called K-space. We'll talk about what K-space is, we'll talk about sort of how we get there, but for now, know at least that this is the so-called raw data collected by the scanner, if you will. And S of K represents a point in K-space, right? K is a vector, and K tells us what point are we at in K-space, right? So we have a 2D matrix, and we can be at some point in that matrix. And the signal at a point in K-space, so how bright or dark that point in K-space is, depends on Faraday's law of induction, which enters in largely through this integration of everything coming out of the object, all of the information coming out of the object. We don't, in the MR experiment, we don't actually resolve what's happening by sampling the signal at a single tiny location that we call a pixel. We instead get information from the entire slice. We'll talk about how we excite slices in a little bit. We get information from the entire slice, and through a specialized encoding strategy, we can actually fill up the Fourier transform space, what we call K-space, in such a way that we can recover an object, an image rather, of the underlying object. So this part we've covered quite a bit at this point. This is the state of the transverse magnetization of the object. We've played some series of RF pulses, maybe some gradients. We've formed a spin echo, we've formed a gradient echo that has a certain signal intensity associated with it. Depends on the tissue's proton density, the T1 and T2. So we have a pretty good sense of how to manipulate the state of the transverse magnetization. The sort of magic, and really what the 2003 Nobel Prize in Physiology and Medicine was for Latimer Mansfield, was really about this term here, the so-called K-space sampling function. How is it that we can take the state of the transverse magnetization, manipulate magnetic field gradients to generate a so-called K-space sampling function that will, the product of these two things gives us a signal that we pick up through Faraday's law of induction that represents the presence or absence of one of these particular points in K-space. How do we change where we are in K-space? Well, fundamentally, we have to change what sampling pattern we're interrogating, right? This expression is saying, take the state of the transverse magnetization, multiply it by some sampling function, add it all up into my receiver such that I get a single amplitude associated with that particular sampling pattern. We call these sampling patterns spatial frequencies. And we can adjust these spatial frequencies by adjusting what we call K. You'll see in a little bit that this K parameter here is really just related to the integral of the gradient waveforms. We can play different gradient waveforms to get different sampling patterns, patterns at different orientations, and patterns with different sort of repetition patterns. And again, these are called different spatial frequencies. If we sample all of these spatial frequencies, then we're filling in all of the different points in K-space, and while maybe not obvious yet, the 2D Fourier transform of that acquired data actually gives us the image of the underlying object itself. So look at this expression later this evening. We're going to talk through sort of where it even comes from in the next kind of 15 slides or whatever, and then try to come back to this. We will at the end of this sort of section or whatever, but come back and try to really understand what those terms are sort of telling us. A question before we sort of go down this path? It's probably not entirely clear at this point, but we're going to get there. Yeah? So one thing to begin knowing or remembering is we have a definition for k-space, right? This isn't derivable per se. This is the definition of k-space. You'll see it come out of the equations a little bit later. The definition of k-space is that where you are in k-space at a particular point in time, when we're playing gradients, gradients move us around through k-space. As a consequence, how long or what the history of our gradient waveform is will tell us where we are in k-space. And that's through this relationship here that just says there's a scaling factor, phi gamma over 2 pi. And it's just the integral of the gradient waveform itself, right? The simplest gradient waveforms, and most of the gradient waveforms we're going to talk about in this class, are just rectangular gradient waveforms like this, right? So this gradient waveform g of t is off at some point in time, we turn it on to some constant amount, and if we wait long enough, then we turn it off again. If we keep track of what's happening to k of t as a function of time, it tracks as follows. At the very beginning, when you have no gradient amplitude and you integrate 0, then you have no k. You haven't moved anywhere in k-space yet. You're still at the 0 position of k-space. And that puts us representationally in the middle of k-space here. As the gradient amplitude is turned on for some finite duration, we've accumulated some area, so we've integrated the gradient over some time, and we have some area. That gives us an amount of k-space. We've moved out a certain amount. And if that gradient's on for, say, twice as long, then we will have moved out twice as far in k-space. And so during the MR experiment, we're going to have gradient waveforms like this that we turn on and that we turn off. While that gradient is turned on, we're going to be linearly moving out in a particular direction of k-space. What happens, for example, if my gradient waveform, instead of being positive, is negative? How's that going to change my k-space trajectory? Right, I see people pointing to the left, right? So I'm just going to move out in the opposite direction, right? I can also, I mean, this gradient is actually a vector quantity, right? Because I can turn on simultaneously any of the x, y, or z gradients, right? So if I want to, I could have been more careful and shown this as a, here I'm calling it the readout direction. The readout direction and the x direction are usually synonymous. So this could have been a g readout, which is what I am showing here. I could have called it the g phasing code, and maybe I was moving instead in the up-down direction. So again, the gradient directly controls, the vector quantity controls where we are as a vector position in k-space itself. So this is an important expression to remember. Yep.
So for this one, is this a frequency encoding gradient?
Well, I mean, it could be. It's not. I'm not really being specific in that sense right now. All I'm saying is that if you turn a gradient on, what's happening physically? So you turn a gradient on. That means across the field of view, there's sort of a high field and a low field, right? And the longer that gradient is turned on for, the more phase will accumulate at the highest edges relative to, say, the middle. And that, in fact, gets you out to higher frequencies in k-space relative to, say, lower frequencies. So this doesn't have to be a readout gradient per se. It's just a gradient. Okay, so that's the first kind of connection to make between how it is that gradients move us around through k-space. So this is a simple pulse sequence, right? This is the gradient echo pulse sequence. And so oftentimes it starts off with, and we'll talk about this in more detail, I don't know if we'll get there today, but we have slice selection. We have to excite the slice that we care about. It's an axial slice, a sagittal, coronal, whatever. So I'm going to excite the slice that I care about. The next thing I'm going to do is I'm going to move around in k-space. How do I move around in k-space? Well, if I apply a gradient that's, say, positive in the phase encode direction and negative in the frequency encoding direction, then I'm going to move positive in the phase encode direction and negative in the frequency encode direction. And so I'm moving out to this point in k-space here. The next thing that happens in the gradient echo sequence is that I reverse the sign of that gradient, and I'm moving across k-space just in the, say, readout direction or just the x direction with no simultaneous y gradient. And that means I'm going to move across k-space in this direction here. This all just comes out of that first expression. What is my k position? It depends on the integral of my gradient waveform. And so we can play slightly different combinations of these gradients to move through different positions in k-space. When I'm moving across k-space in this linear fashion, having excited a slice, dephased, and now rephased with this gradient here, I'm moving linearly across k-space. That will help me form an echo. And so in the gradient, you saw this in the gradient echo sequence. That was when we were able to form an echo. Which echo you're actually forming depends on how far you've moved along, say, the phase encoding direction. Meaning, did you move far out in k-space this way, or maybe far out in the negative direction? We can control which line of k-space we're moving across. What's our trajectory? And so the amplitude of this signal, we talked about this before, is just coming from the gradient echo expression. What's our TB, what's our TR, what's our T1, T2 star, flip angle, those kinds of things. That's going, the signal that I acquire at that point in time, given that I'm moving left to right across k-space, will fill this line of k-space with information governed by the gradient echo signal equation. Now, in sort of subsequent steps, it goes something like this, right? I don't move as far out in the phase encode direction. I move out just as far in the frequency encode direction, and then I turn on a positive gradient to move from left to right again. And in this case, because my phase encode gradient was, say, half the area, I only moved out half as far, and then I read out across from left to right. Now, this still probably isn't really concrete. Like, what am I really doing? The concept I'm trying to get across right now is just this relationship between gradient waveforms and movement through k-space. And it all happens as a consequence of that integral equation that I showed you on the previous slide. And so the conventional sequence, say the gradient echo sequence at least, moves through these kinds of steps, right? We're manipulating the area of the phase encoding gradient. We're keeping the readout or the frequency encoding gradient waveform constant. So this is really the only thing that's changing from echo to echo to echo. And it just means that I'm able to acquire or move through a different line of k-space, right? I either moved out very, in the positive sense or in the negative sense, so I can sweep through different points in k-space. Now, what's not obvious, we haven't talked about sampling criteria and so forth yet, so it's not obvious, but a point is that we have to acquire a certain number of lines of k-space that accord with the imaging resolution that we ultimately want to have for the object that we're trying to resolve. And so this is a simple example of 5 lines. Oftentimes we need way more than that, right? 128 lines or 256 lines if we want to have a high quality image. So this is just an example. So, yep.
I had a question. Is the k-space usually taken one way, or can you do one way and then the next way
Yeah. Yeah, you can do that. So let's talk about how you would do that first, right? So I think what you're saying is that for this, let's call it the red echo. The red echo goes left to right, and I think what you're asking is, could I also go right to left?
Yeah.
Yep. So yes, you can. How would you do that? What would you have to change?
You would
Yeah. And so this one, instead of going out, this is taking us in the negative direction, so it's coming out, say, this way. But we want to go in the positive direction first, and start off way over there, right? And then we have this readout gradient that we have to flip over also, so that instead of going from left to right, we go from right to left.
Is there any difference in the...
There are differences. It depends exactly on what you're trying to do. So if what you did was reverse this for all echoes, right? So that every echo was, instead of left to right, was right to left. Those two images would be quite similar. If, on the other hand, what you did was change such that half of your echoes were left to right and the other half were right to left, that can create some headaches for you. And that's as a consequence of everything from very subtle timing differences in the gradient subsystem, like every little point in k-space maybe doesn't perfectly line up. If there's a delay in anything here, they're just all shifted, and that ends up not really mattering that much. But if you have 2 echoes that are shifted relative to one another, that can actually create aliasing effects. So there's maybe a much more complicated sort of answer there. In general, we try to avoid doing that, but it can, in fact, be a very fast-weighted image as well. So hard to give a neat answer. It's a good question. Okay, and so I'm not sure exactly why I'm showing that image, but the point is that were you to acquire all of the sort of necessary lines of K-space, then you could reconstruct the image that you cared about. The governing principle, something to keep in mind, is that if your image is say 256 by 256, then the K data that you have to acquire also needs to be 256 by 256. There's a one-to-one sort of information mapping between Fourier transform space and image space. We need to have the same number of data points, if you will. So this I alluded to much earlier, but it's coming up now again. So here is how do we even think about calculating the scan time, right? It's relatively straightforward. Obviously, an important parameter is the TR, right? How long does it take to acquire an echo? Typically, we're getting 1 echo per TR. There's exceptions to that. MR's got lots of flexibility, but let's keep it simple for now. So it's the TR times the number of phase encoding steps, right? And so if we go back to this guy here, I've got 5 phase encoding steps, right? Well, I might have 128 phase encoding steps, or 256 phase encoding steps, whatever. Depending on how many phase encoding steps you need to resolve the image to your satisfaction, that's going to take longer and longer, right? And so it's simply the TR times the number of phase encode steps. And if your image quality overall is kind of fair at that point, meaning it's noisy, you can just repeat the acquisition. We call those averages. And so you could just do 2 averages or 4 averages. We'll talk about the pluses and minuses of doing that, but obviously if you repeat it twice, it takes twice as long. And so, again, typically 1 phase encode step per TR. Each phase encode step requires just a simple echo, 1 echo. And if we're going to acquire, say, 128 echoes, it really depends on what your TR is. If your TR for a spin echo sequence is 2,500 milliseconds and you need 128 echoes, it can easily take you 5 minutes to acquire an image, right? Now, this is just an example, right? There are lots of ways that we can manipulate what the TR is or how many lines we actually need to get the image quality. But this is one way of just pointing out that imaging with MR can be slow. And the consequence that's being shown here on the bottom here is that as we reduce the number of K lines, now we're just getting these middle lines, we're getting a crummier and crummier image, right? So the farther out we go into K space, these are so-called high spatial frequencies. And the high spatial frequency information is what gives us the really high resolution information. Obviously, clinicians, scientists typically want high resolution information. And so we have to go out far enough into K space to get an adequately resolved image. Whereas if we really just get the central lines of K space, we get this really blocky looking image that is not likely to be useful. Yep.
So then does the frequency encoding, is that what determines your Y resolution? Like how long your gradient stays on?
So so let's talk about left-right as the readout direction, right? The number of points you sample is what's going to dictate the resolution. So it's sampling points, if you will. Okay. So that equation that I showed you sort of 4 or 5 slides ago, which was the MR signal equation, the question is, well, where does that even come from? It's maybe a little bit difficult to understand to begin with, but let's at least try to get some traction on where it came from. And the derivation, again, is in the online slides. The idea, and some of this you're familiar with already, right? An RF pulse manipulates the spin system to create some state of transverse magnetization. You can sort of appreciate that once I have transverse magnetization and I have a coil, I can get a voltage in that coil. What happens next is sort of procedurally a little bit on the complicated side, but it really ends up in the final result of having this K-space data coming out of this voltage signal. What's the frequency of that voltage signal? Is it high or is it low? Well, when we're first starting out, right? So I'm just magnetization processing at what frequency? Larmor frequency. How fast is that? Fast. Good answer. Megahertz, right? Tens of megahertz, right? That's fast, indeed. And so this signal here is really cooking, right? This isn't my k-space signal yet, right? If I've done the experiment correctly, I've manipulated the transverse magnetization, I've somehow stored position information or spatial information, but that's still zipping around at 64 megahertz. The process that happens next is a combination of things. It's first detecting net voltage through Faraday's law of induction. We'll look at that because that depends on the state of the magnetization, but also your coil, right? If you have a crummy coil, you're not going to measure that voltage very well, right? Certainly not its amplitude. It's going to be noisy. You're going to have a low amplitude signal relative to the noise floor. So we need good coils, right? We need to know the state of the we want to recover the state of the transverse magnetization. We need to have a good coil. If we want to make sense of that voltage information, which is really can tell us about the precessional frequency and phase of the transverse magnetization, then we need to use what's called phase-sensitive detection. And we'll talk about why that's important. One thing that phase-sensitive detection does is it gets rid of that baseband, or at least this process here of phase-sensitive detection, will take us from a laboratory frame signal, right? In the laboratory frame, we're at 64 megahertz. We don't really care about that, right? We never really care about the B0 component of the frequency. What we actually care about is the delta frequency. How different are we from the B0 frequency? You'll see this, but this is how we store and encode the spatial information, the imaging information, if you will. So this process of phase-sensitive detection actually takes us from a laboratory frame signal to a rotating frame signal. And that's not obvious, but I'll show you some of the higher level steps for that. Eventually, we go from this voltage signal through this phase-sensitive detector in the mixer to this S of T. S of T is not quite to K-space. S of T is a signal now. It's not a voltage, at least in very loose language, right? It's a signal. It's actually a complex signal. We've used two phase-sensitive detectors so we can actually detect the frequency and phase of the transverse magnetization. So that we know it's rotating clockwise or counterclockwise, and what's its phase relative to some clock that we're using. Then there's another step where we can say, well, I know what that signal is doing as a function of time, and what it's doing as a function of time depends on the gradients I was applying. And the gradients I was applying are related to K-space. We saw that 4 or 5 slides ago. And so then there's a step where we can go from this complex signal to finally having an S of K signal. What is the signal intensity for a point in K-space? And we can get a string of points in K-space and fill up our whole K-space array. This is the goal. How do we fill up the K-space array, and how does the signal that we actually generate give us points in K-space? And then we've said it a few times, and it's still not obvious probably from the material we've covered in this class, but it will be, or you will come to see that it's the 2D Fourier transform of this so-called K-space that finally gives us an image of the underlying object. So I is a function of the object. Are you guys comfortable with maybe two concepts right now? One is if I'm saying that the transverse magnetization is a function of space and time, right? Obviously, every pixel, every location has its own state of transverse magnetization, and that can change as a function of time. And then I use this to represent the image, right? The image itself is a function over space, right? R is just some position vector somewhere inside of this object, if you will. The other thing to appreciate is what is S of K pointing to or referring to? Having just kind of gone through this just now, does someone want to give a stab at what is S of K? It is, yeah, no, that's a great definition. And so the S of K, she said it really nicely, it's the presence or absence of I think you said a specific banding pattern. So if we go back to that signal expression I had 4 or 5 slides ago, there's sort of banding patterns, and through the application of different gradient waveforms, we can create different banding patterns in our underlying object. Whether or not that banding pattern is present or not in the underlying object is something that we're measuring. And if it's high, then then the signal for that particular K will be high. For example, in the middle of K-space here, these are high signal values. But out at the, say, edges here, they appear to be relatively low K values, and so that spatial frequency is less well apparent in that particular object. We'll go through this a half dozen times at least, because these are some relatively opaque concepts, I think. Another way of saying it is S of k is just telling me about the amplitude of a particular point in k space. My k vector, right? I'm somewhere in the kx, ky axis. So that k vector just tells me where I am in this space. And the s just says what's my amplitude for that particular point in space. If you're super into the signal processing aspects of this, it's not just the amplitude, there's also a phase component to all this. We speak sometimes loosely about just the signal amplitude itself. Okay, so how do we even get started with this? We know, just going back to, say, physics, that voltages as a function of time depend on the time derivative of the flux, right? Now, a concept that's hard to motivate sort of very directly is the idea that the voltage that we receive depends on this expression here, which contains two main terms. One is what we call the B receiver field. So the receiver coil itself has a specific ability or sensitivity for detecting signals. And we'll talk about this a little bit more. But think about this as being basically the sensitivity of the receiver coil. Okay? We can have good coils and we can have bad coils. I'll show you some pictures of this in just a second. The second component of it here is the state of the magnetization. And not just the transverse magnetization, but sort of all of the magnetization. It's just a dot product. And so if our B field and our transverse magnetization are parallel to one another, then we'll have nice strong signals. And if they're perpendicular, then we won't have a strong signal. So what happened in the online sort of derivation was more discreetly describing what do we mean by coil sensitivity. The coils themselves, we build, manufacture better and worse coils, right? The coil itself has a magnitude associated with it, which is sort of how strong or how good of a job does it do of picking up nearby signals. But the magnitude itself can also, or the receiver system itself can also add a phase to the signal. So you'd like it to be the case that maybe your coil doesn't add any phase to your signal, but it's an imperfect world, and so it will add some phase. We also have the bulk magnetization term that's on the right-hand side here. It's a full vector. It's not just the transverse magnetization. It's the x and y and z components of the magnetization. In that derivation, what you would find out is that the time rate of change of the z magnetization is really slow, right? So you think of mz recovery, right? mz is recovering on the scale of like hundreds of milliseconds or even 1,000 or more milliseconds, right? Dependent on t1, right? The time rate of change of mx and my is way faster, right? mx and my are zipping around at 64 megahertz, right? These are microsecond phenomena, right? And so it turns out that the time rate of change of the z flux is really small compared to the transverse flux. And so we end up not having to concern ourselves with that specific term. And that's actually a really important concept, right? Because what it means is that the magnetization that we detect, or the voltage that we detect, is really just dependent on the transverse magnetization. We've been saying that, but that's not necessarily an obvious concept. What it boils down to is that if my iPad is my coil and this is my magnetization, my XY magnetization is going very, very quickly past my coil, right? And so its time rate of change is high, whereas my MZ magnetization is doing something really, really slowly. So it's inducing a flux in that coil, but it's so tiny compared to the transverse magnetization components that it effectively drops out. And so this is a hardware component, right? This is the receiver coil, and this is the state of the transverse magnetization at the point that we're trying to detect the signal, right? So when we're detecting signals, we're doing that at times of what we call free precession, right? We've stopped playing RF pulses. We might be playing a gradient, but we're not forcing the system to do anything. We force precession with RF pulses. So during a period of free precession, we're just listening to the transverse magnetization, or the magnetization at all. And how's that described? Well, the state of the transverse magnetization depends on its magnitude. So you've done something to play RF pulses to manipulate how much T1 contrast, how much T2 contrast you have at that point in time. As soon as you have generated that state of the magnetization and you've tipped into the transverse plane, it's also subsequent to additional decay, right? So as soon as you have your favorite T1 contrast and you tip it to the transverse plane for imaging, that signal is going to decay as a function of T2. It's going to be processing around at the Larmor frequency, and it's going to have a phase that comes from, say, the transmit system, the RF phase that you put into the transverse, into the magnetization itself. So this is a sort of a complete description of the state of the transverse magnetization at the time we're trying to detect it. And the longer we are trying to detect it, the more that signal decays. And you saw that in the echo signals. The echo signals are decaying as a function of time. They're strong, but they're getting weaker, right? And so this is the maybe most complete description for the state of the transverse magnetization. Then the full derivation is complicated. There's a lot of trigonometry, there's a lot of algebra, and it ultimately boils down to this, that by the time we take the time derivatives, there are no time derivatives for the hardware component, the B field, it's just a constant hardware thing. So we just have to take the time derivatives of what's happening in the transverse magnetization, but this component we said is small. So that sort of helps simplify a bunch of terms, and then there is a bunch of this sines and cosines nonsense, right? What it leads to is finally this expression here, and this is worth, you should be able to look at this and sort of talk about what these terms mean, right? So if you see this expression on the final and I say, you know, explain to me what each of these terms mean, you should have that level of understanding. I'm not going to ask you to derive this, right? I really want you guys to have the tools to go back and figure these things out. They're really important, especially if you're going to be an MR scientist. But for the purposes of this class, this expression really, I want you to understand the terms. And so we're going to talk through these terms right now, and then, of course, questions are fine. So the voltage that we detect is coming as the voltage that your coil receives depends on the integral of the whole object, right? We're not getting the signal from a pixel. We're not getting the signal from some tiny little location. We're getting the signal from everything that was excited, right? Our coils are really pretty dumb that way, right? There's some tricks now that are a little bit different, but to sort of first approximation, our coils just receive whatever we excited. And we typically excite a slice, and so the coil just says, fine, I'll listen to the whole slice for you. And that's what the integral means. I'm going to listen to the whole object, whatever you excite, the slice. What you see next is just that there's a frequency dependence, and that frequency can be made a function of space. We know that when we turn on gradients, for example, that we can make frequency vary over space. So we'll see the importance of this term a little bit later. The second term here, there's an amplitude brackets, right? So it's the absolute value of what we call the B receiver field. This is the sensitivity of the coil. We can have good coils, we can have bad coils. If I have a good coil, then this term is going to be big. If I have a bad coil, then this term is going to be small. Interestingly, this receiver B field can be spatially dependent. And that's not too surprising. That means that the coil is sensitive to some things that are close to the coil, and less sensitive to things that are distant from the coil. And so the receiver sensitivity for the coil has a spatial dependence. It doesn't have a temporal dependence, right? Coils are stable. We don't think of them as changing as a function of time, but it does have a spatial dependence. The next stuff we talked about a little bit. It's the state of the transverse magnetization. Transverse magnetization decays as a function of at least T2 when you start listening to it. And then there's a phase term on the end here. And there's some things in the phase term we care about and some things that we don't care quite as much about. One term that we care a lot about is this omega R term here. This is frequency being a function of space. Frequency being a function of space should be pointing out to you guys this concept of spatial encoding. We haven't gotten all the way there yet, but when you see frequencies depending on space, that's related to storing spatial information, or actually performing the imaging experiment. And we'll see how gradients and k-space sort of come into this component here a little bit later. The last couple terms are constants. It had a slightly different term here. It really should be phi RF and phi E are the same. RF is the B1 field. E is the exciter field. And so those would really just be the same. When you play an RF pulse, it has a phase, and so and that phase could in fact be a function of space. Your B1 coils are not perfect, and so they can add, you have a target phase, but the amount of phase you actually get can vary over space. We also have the receiver phase, right? So just like we had the B field sensitivity, or the coil sensitivity rather. There's also a so-called coil phase, or the receiver phase. And then there's a constant term that pops in there when you work through all the whole derivation. Constants we don't oftentimes care too much about. So again, it'll take some work, but it'd be useful, I think, to be able to talk about what each of these different terms mean. Questions as I've just gone through that?
Can you go through the cosine part here? Just,
Each of the terms?
yeah.
Yeah. So the first term here is going to be related to spatial frequency encoding, or the actual like imaging experiment, if you will. Everything before, let's look at everything before it, right? So there is an omega term here. We'll come back to that one. This is the coil term. This is the transverse magnetization term. This is the decay of the transverse magnetization. Then you have a spatial frequency encoding term, and then you have phase from the RF pulse, phase from the receiver, and then this kind of annoying constant term pops in. Okay, so let's look at an example of the excuse me, of the coils themselves. So when we do an imaging experiment, oftentimes we have several coils, right? In this example, let's just assume we have two coils. We have maybe it's an anterior coil and a posterior coil. This is an example. We can measure these things. This is an example of the B receiver amplitude, right? The coil sensitivity for coil 1 and coil 2. So let's assume this is an object, right? Let's assume it's a head or something like this, right? I have a coil that's near my object in image 1 and near my object in image 2. Spatially, where do you think the coil is positioned relative to the object in this image here? Top or on the bottom or on the top? On the bottom, right? If I have a coil close to my object, I'll get the strongest signals, right? So a coil on the bottom here will have a receiver sensitivity that's high, close to the bottom, and it's lower as you get farther and farther away from the coil. Makes sense. I can't pick up signals that are farther and farther away from me. So then hopefully it's a gimme. On the right-hand side, I have a second coil. Is that coil positioned on the top or the bottom? On the top, right? So MR scientists have figured out, hey, you know what? This is actually kind of interesting. I should probably use lots of coils. And that's basically what we do now. We use 16 coils or 32 coils because we can, I'll show you later, but we can add up the information from multiple coils to get a more homogeneous object. But the voltage that you receive, right, if we go back to this expression, the voltage that you receive depends on the sensitivity of your coil, right? If your coil is so good that it's perfectly uniform sensitivity over the whole object, then your voltage is going to be higher, right? If your coil is crummy because you made it last night and you're trying to use it for your abstract that's due tomorrow, and the signal intensity is low everywhere, that's because your B receiver field is low everywhere and the quality of your coil is not so high, right? Usually these things make sense in the magnitude space. We can understand that if a coil is near the object, it's going to be stronger and it's going to fall off as a function of distance, right? What's not always as obvious is what happens to the phase. So the receivers, they have a magnitude and they have a phase associated with them. So when they're picking up signal, they're coloring the signal with some magnitude information. They're also coloring it with some phase information. And the phase patterns can be complex and they're harder to understand. But you should at least recognize that when the coil does its listening, it affects both the magnitudes of the underlying signals themselves and the phase of the underlying signals themselves. And if you don't deal with both the magnitude and phase information correctly, then you can end up with sort of poor image quality in your reconstruction. That's a useful example. Yep. So here's just a slightly different example. So imagine you've got a person here, there's 4 coils, 2 anterior coils, and then there's 2 coils placed posteriorly. And each coil just has a slightly different view, in this case, of the heart, right? So they're closer to some anatomical regions than others. They all 4 coils had different B receiver fields, right? They had different coil sensitivities. They might be manufactured to be, nearly identical, but just as a function of where they're positioned in the scanner relative to the object, their B field as a function of space will be different. What happens to make a better image is that there's ways of combining, we'll talk about this at the very end if we have time, we won't have time, is that we can combine these 4 images together to get a more uniform image through the compositing of these 4 different coil images. So let me talk through a couple more steps because that'll help us stay a little bit more on track, and then we'll call it quits here in just probably 5 minutes or so. So you have a pretty complicated voltage signal at this point, and it's a very high frequency voltage signal, right? It depends on your Larmor frequency, which may in fact depend on space as well. The process, and there's sort of two things that you want to get out of this voltage signal. You want to know something about its magnitude, because the magnitude tells you something about the strength or weakness of what's happening inside your object. But you also want to know something about its phase. In phase, there are ways of detecting, is my magnetization, if I just have a coil, say the iPad's my coil, and this is my magnetization, and it's just zipping around, if I get an amplitude out, that's fine. That tells me about the amplitude of my transverse magnetization. But if what I really want to know is where is my transverse magnetization, is it over here, is it over here, then you have to use what's called phase-sensitive detection. Phase-sensitive detection is not really that complicated. It's basically taking this rather complicated voltage signal and just multiplying it by a cosine or a sine, and a specific cosine or sine, one that's a function of the Larmor frequency. And what that's really going to help us do in combination with the low-pass filter is go from this voltage signal, which you maybe have some intuition for, to what I'll call S of t. And S of t is kind of an intermediate signal. We don't really deal with it per se, because it's just an intermediate step to getting to that S of k signal, the one we really care about. But this S of t signal, what its advantages are is a complex valued signal, so it has real and imaginary components, if you will. And what that means is you can detect both the magnitude and the phase of the transverse magnetization. And that becomes important to us, because oftentimes we actually care about the phase of our magnetization. And so I won't go through sort of all of the steps of how this actually boils down, but we're going to take that voltage expression, multiply by a cosine function, or multiply by a cosine function, a sine function, put it through what we call a low-pass filter. The low-pass filter says keep the low stuff, toss the high stuff. When we toss out the high stuff, what we're getting rid of is basically the Larmor frequency. And when we get rid of the Larmor frequency, we're actually doing a transformation in coordinate systems, right? So we're going from that laboratory frame to the rotating frame. And in all of MR, not all, but 99% of MR, what we really care about is just the rotating frame signal. And so this rather complicated process of going through the phase-sensitive detection and low-pass filters finally gives us this S of t signal, which is arguably a little bit simpler. And it just looks like this. We're going to add those two signals together, so it's a complex valued signal. It has a constant term in front. Again, we're still just integrating over the object. Our coils are dumb. They just listen to everything that we excited. And at the point at which we're measuring and sampling our S of t signal, it depends on, I won't go into it right now, but it still depends on the B receiver field, the state of the transverse magnetization, and now you see more clearly the so-called spatial frequency encoding term. If you go all the way back to the signal equation that we showed 10 or 8 slides ago or whatever, there was a term that looked a little bit like this. It was the state of our transverse magnetization multiplied by an exponential term that looked a little bit like this. It had a k in front of it instead of a delta omega, it had a k. We're gonna get there at the beginning of next lecture. But the point is that going through this process gets us into a complex valued signal in the rotating frame, and you can begin to see maybe where the spatial frequency encoding starts to pop in. This is probably the last, I'll maybe click through one more time. So this delta omega, what is delta omega? Delta omega is a deviation from the Larmor frequency, right? Everything's happening at the Larmor frequency, but we sort of don't care about that. That's useful for detection principles, but it's not useful for actually image formation itself. What image formation itself depends on is a small variation in the Larmor frequency, the so-called delta omega. And the small variation in the Larmor frequency is a function of space. When I turn on a gradient, I have a range of frequencies across my object. The range of frequencies that I have depends on the gradient that I've applied, and then, of course, the spatial position. How far away am I from isocenter? I'll have higher and higher frequencies. And if you go back to our k-space definition, we can relate the gradients that we've applied to the position or point we are in k-space itself. And so the last sort of substitution here allows us to go from this kind of intermediate S of t signal, this complex value rotating frame signal, to this S of k signal, which is telling us again the amplitude and phase for a particular point in k-space depends on now something that looks like that expression that we sort of started with, right? Integrating over the object, our coils are dumb, they just listen to everything coming out of the excited volume or slice. The state of the transverse magnetization, and now the spatial frequency encoding term here. And this is the delta omega that we first saw popping up here. So there's a lot of steps there, right? And I don't, for the purpose of the final or your homework, you're not going to be deriving these things, but I do want you to have some, backbone for where did this thing even come from. We're going to have to dig into this some more. I'll show you one last slide here, just as the summary of the signal equation again. So you have some object. I think we understand well now how to manipulate the state of the transverse magnetization. What's still a little bit mysterious, and we're going to come back to, is how we sort of manipulate or change these spatial frequency terms. Through the application of gradients, we can pick these spatial frequency terms. And at a particular point in time, we're picking a spatial frequency pattern. That's multiplied onto our object. We can pick that up into our coil, and it tells us about the amplitude of that particular spatial frequency. That's procedurally how it happens. I still need to give you more sort of insight, more depth to understanding sort of why this works at all. But that's where we're headed, so that you can eventually appreciate that this S of k tells you what's happening at a particular point in k-space. And our job is to move around k by changing our gradient waveforms. We can move through k-space in different ways, actually, all kinds of different ways. It just depends on the gradient waveform, so that we can sample each of these different points in k-space. And then, finally, the FFT, or the Fourier transform, will give us back the image of our underlying object. That's a lot. I know it's kind of a lot to absorb. So go back, check out the material online, ask me questions, and really try to think carefully about what you think this expression means. We'll probably start with that next time, sort of having a conversation about it, and then looking at the math. Okay? But thanks, guys, for sticking it out.